Welcome! In this session, we'll dive into problem number 704, titled Binary Search. It's a classic problem that tests your understanding of one of the most efficient searching techniques. We'll go over the problem statement, discuss possible approaches, and analyze their complexities. Let's get started. The problem is to implement a binary search algorithm to find the index of a target value within a sorted array of integers. If the target exists in the array, we return its index, and if it does not, we return -1. Binary search is an efficient algorithm that works by repeatedly dividing the range of possible values in half. Importantly, the input array is guaranteed to be sorted in ascending order. The function will take two inputs, nums, which is the sorted array, and target, the integer value we are searching for. The output will be the zero-based index of the target if it exists, or -1 if it does not. This forms the core of the problem we need to solve. Let's consider the first example. Here, the array nums is -1, 0, 3, 5, 9, 12, and the target value is 9. Using binary search, we start with the entire array. The middle element is at index 2, which has the value 3. Since 3 is less than 9, we discard the left half of the array and focus on the right half. The new search range is 5, 9, 12. Now, the middle element of this range is at index 4, which is 9, matching the target. Thus, we return 4, the index of the target in the array. In the second example, the array nums is the same, -1, 0, 3, 5, 9, 12, but the target value is 2. Using binary search, we start by looking at the middle element at index 2, which is 3. Since 3 is greater than 2, we discard the right half of the array and focus on the left half. The new search range becomes -1, 0. The middle element here is at index 0, with a value of -1. Since -1 is less than 2, we discard the left half, leaving 0. The middle element of this range is at index 1, which is 0. Since 0 is still less than 2, we discard this as well. Now, the search range is empty, indicating that the target does not exist in the array. Therefore, we return -1. Now, consider the third example where the array nums contains only one element, 5, and the target value is also 5. Here, the middle element is at index 0, and its value is 5, which matches the target. Since the target is found immediately, we return 0, the index of the target in the array. This example demonstrates how binary search behaves when the array has just one element, making it a simple and direct case. Finally, let's look at the problem constraints and edge cases. The array nums will always have a length between 1 and 10,000, and all integers in nums and the target will fall between -10,000 and 10,000. Importantly, all elements in nums are unique and sorted in ascending order. Some edge cases to consider include when the target is smaller than the smallest element in nums, such as nums equals 1, 2, 3, and target equals -1, or when the target is larger than the largest element, like nums equals 1, 2, 3, and target equals 10. Additionally, the target might be the first or last element in the array, such as nums equals 1, 2, 3, with target equals 1 or target equals 3. These scenarios help highlight the robustness of the binary search approach. To solve this problem, the first approach we could consider is the brute force method. Here, the idea is to perform a linear search starting from the first element of the array and checking each element one by one to see if it matches the target. If we find a match, we return its index, otherwise, if we reach the end of the array without finding the target, we return -1. This method is very simple and straightforward, but it completely ignores the fact that the array is sorted. While it works, its time complexity is O(n), which means that as the array grows larger, the time needed to search increases linearly. With arrays that can have up to 10,000 elements, this approach becomes highly inefficient. Additionally, it uses no extra memory, making its space complexity O(1). However, for large datasets, the inefficiency in terms of time makes this approach unsuitable for our needs. A more efficient solution is the binary search method, which takes full advantage of the sorted nature of the array. Here's how it works. We start by defining two pointers, one pointing to the beginning of the array, called left, and the other pointing to the end, called right. Next, we calculate the middle index of the array using the formula mit equals left plus right left, //2. We then compare the value at this middle index with the target. If the middle value matches the target, we return the middle index. If the middle value is less than the target, it means the target must be in the right half of the array, so we move the left pointer to mid +1. Conversely, if the middle value is greater than the target must be in the left half, so we move the right pointer to mid 1. We repeat these steps, continually having the search space until the pointers cross. At that point, if no match is found, we return -1. The key insight here is that by eliminating half the search space with each step, the algorithm operates in O log n time, making it exponentially faster than linear search for large arrays. This is why binary search is a much better fit for this problem. Given the constraints and the size of the array, we chose binary search as our strategy because of its exceptional efficiency. For an array with 10,000 elements, binary search only requires about 14 steps to locate the target, compared to 10,000 steps for a brute force linear search. This dramatic difference in performance is crucial for solving problems within competitive programming time limits. When comparing binary search to linear search, binary search is faster but requires the array to be sorted. On the other hand, linear search works for any array but is far slower for large datasets. We also considered the iterative versus recursive implementations of binary search and decided to use the iterative version. This avoids the overhead associated with recursive calls and eliminates the risk of a stack overflow in cases where deep recursion might occur. By leveraging the sorted property of the array and focusing on efficiency, binary search is clearly the optimal choice for solving this problem. To solve the problem of finding the index of a target value in an array, the algorithm begins with a straightforward linear search approach. The task is to systematically check each element of the array until the target value is located or the entire array is traversed. First, we initialize an input array ARR of size n and a target value x. A variable named index is set to -1 to store the result, ensuring that if no match is found, index remains -1. The next step involves iterating through the array using a for loop. For each element, we compare the current value ARR, I, to the target value x. If the two values match, the algorithm identifies the position of the target value and updates index to the current index I. This basic setup forms the foundation of the linear search process. When a match is found during the search, the algorithm immediately exits the loop using a break statement. This optimization eliminates the need to continue checking the remaining elements, which saves unnecessary computations. Once the loop concludes, the value of index is returned as the result. If a match was found, index will contain the position of the first occurrence of the target value. Otherwise, it will remain -1, indicating that the target value is not present in the array. This approach works well when the array is unsorted, as linear search guarantees a solution within O n time complexity. Additionally, the algorithm is optimized for early termination, which improves efficiency when the target value is located earlier in the array. Key edge cases include an empty array, where the function directly returns -1 without executing the loop, and situations where the target value is absent, leaving index unchanged. These conditions ensure the algorithm handles all possible scenarios gracefully. The algorithm also considers arrays where the target value appears multiple times. In such cases, only the index of the first occurrence is returned. This behavior is a natural result of the sequential nature of the search process. The input array serves as the primary data structure, allowing indexed access for efficient traversal and comparison. The variable index plays a crucial role in storing the result, making it possible to return either the correct index or -1 if no match is found. The algorithm relies on three key operations. First, the comparison operation, ARR, I, == x, is performed once for each element in the worst case. Second, the assignment operation, index = I, occurs only when a match is found. Finally, the early exit mechanism using break ensures that unnecessary iterations are avoided, further enhancing the efficiency of the algorithm. Together, these steps and operations provide a solid framework for solving the problem. Now let's analyze the complexity of this algorithm. The time complexity is O n, where n is the size of the array. This is because, in the worst-case scenario, the algorithm needs to traverse all n elements to determine whether the target value is present. The space complexity is O(1), as the algorithm only uses a constant amount of extra memory for variables like index. To better understand how this algorithm operates, let's walk through an example. Consider an input array ARR equals 4, 2, 7, 1, 5, and a target value x equals 7. The algorithm initializes index equals -1 and begins iterating through the array. It compares the first element, ARR 0 equals 4, with x equals 7, no match. The process continues with ARR 1 equals 2, still no match. When it reaches ARR 2 equals 7, the target value is found. The algorithm sets index equals 2 and exits the loop early, as further comparisons are unnecessary. Finally, the algorithm returns the value of index, which is 2 in this example. This indicates that the target value 7 is located at index 2 of the array. If the target value had not been present, the algorithm would have completed the loop without finding a match, and index would remain -1. This straightforward example demonstrates how the algorithm efficiently locates the target value and handles both positive and negative cases. By combining simplicity with early exit optimizations, the linear search approach provides a robust solution for finding the index of a target value in an unsorted array. This Python solution implements binary search to efficiently locate the index of a target value in a sorted array. The function begins by defining two pointers, left and right, to represent the search boundaries. These pointers are initialized to the start and end of the array, respectively. Inside a while loop, which continues as long as left is less than or equal to right, the midpoint index is calculated using mid equals left plus, right left, //2. This avoids potential integer overflow issues with large indices. Next, the algorithm compares the midpoint element, nums, mid, to the target value. If nums, mid, equals the target, the function immediately returns mid, the index of the target. If nums, mid, is less than the target, the search range is shifted to the right half of the array by updating left equals mid plus 1. If nums, mid, is greater than the target, the search range is shifted to the left half by updating right equals mid 1. If the loop exits without finding the target, the function returns -1, indicating the target is not present in the array. This implementation ensures an O log n time complexity, making it highly efficient for large datasets as long as the input array is sorted. This is the Java implementation of the binary search algorithm for LeetCode problem number 704. The logic mirrors the Python implementation, with some Java-specific differences such as type declarations for the method parameters and the array. The algorithm uses a standard binary search approach, repeatedly having the search space until the target value is found or the search space is exhausted. The key difference lies in Java's syntax and the absence of Python's dynamic typing. In this example, we are tasked with finding the target value 9 in the sorted array nums equals -1, 0, 3, 5, 9, 12. We start with the initial state where left is 0, and right is 5, representing the indices of the first and last elements. To narrow down our search, we calculate the middle index using the formula mid equals left plus, right left, //2, which results in mid equals 2. The value at this index is nums, 2, equals 3. Comparing this with the target, we see that 3, 9, meaning the target must be in the right half of the array. To focus on this half, we update left to mid plus 1, which is 3. In the next iteration, with left equals 3 and right equals 5, we calculate a new mid as 4. The value at nums, 4, is 9, which matches the target. Therefore, the target is found at index 4, and we return 4 as the output. Now, let's look at an example where the target is not found in the array. The input array remains nums equals -1, 0, 3, 5, 9, 12, but this time the target is 2. Initially, left is 0, and right is 5. Calculating the middle index gives us mid equals 2, and the value at nums, 2, is 3. Since 3, 2, we search the left half of the array by updating right to mid 1, which is 1. In the next iteration, with left equals 0 and right equals 1, we calculate a new mid as 0. The value at nums, 0, is -1. Comparing this with the target, we see that -1 2, so we now search the right half of this smaller range by updating left to mid plus 1, which is 1. Continuing the process, with left equals 1 and right equals 1, we calculate mid equals 1, and nums, 1, is 0. Here, we compare nums, mid, which is 0, with the target 2. Since 0, 2, the target must lie in the right half of the array. We update left to mid plus 1, which becomes 2. At this point, left is greater than right, 2 greater than 1, indicating that the target value is not present in the array. As a result, we return -1 to signify that the target was not found. Now, let's consider a different scenario where the target is found at the very beginning of the array. In this example, the input array is nums equals 2, 5, 8, 12, 16, and the target is 2. Initially, left is 0, and right is 4. Calculating the middle index gives us mid equals 2, and the value at nums, 2, is 8. Since 8, 2, we search the left half of the array by updating right to mid 1, which becomes 1. Next, with left equals 0 and right equals 1, we calculate a new mid as 0. At this index, nums, mid, is equal to nums, 0, equals 2, which matches the target value. This means the target is found at index 0. Therefore, we return 0 as the output. This demonstrates how binary search efficiently narrows down the search space and finds the target, even when it is located at the beginning of the array. By repeatedly having the range, binary search ensures that we achieve optimal performance in finding the target or determining its absence. The time complexity of the binary search algorithm is O log n, and this is largely because the search space is halved with every iteration. To begin, the entire input array, which contains n elements, is considered as the search space. In each step, the algorithm calculates the midpoint of this space, which only takes constant time, O1. After this, it compares the value at the midpoint with the target. If they are not equal, the algorithm adjusts either the left or right pointer, effectively reducing the search space to half its previous size. This halving process continues until the search space is reduced to a single element or the target is found. Since the number of halving steps required is proportional to the base 2 logarithm of n, the total number of iterations is at most log_2, n, plus 1. As each iteration involves a constant amount of work, the overall time complexity is O log n. In the best case, the target is found in the first comparison, resulting in a time complexity of O1. In the worst case, the search continues until the search space is completely exhausted, which gives us the O log n complexity. On average, this halving process still dominates runtime behavior, so the average case time complexity remains O log n. The space complexity of binary search is O1, which means it uses a constant amount of extra memory. This is because the algorithm only requires a few variables such as left, right, and mid to manage the search process. These variables occupy the same amount of memory regardless of the size of the input array. Importantly, the algorithm does not modify the input array, nor does it create additional data structures like recursion stacks or dynamic arrays. This keeps memory usage fixed and independent of the size of the input. As a result, the space complexity remains constant at O1. When comparing binary search to a naive approach such as linear search, the efficiency of binary search becomes clear. In a linear search, each element of the array is checked sequentially until the target is found or the array is exhausted. This results in a time complexity of O(n) in the worst case, since all n elements might need to be examined. Binary search, on the other hand, reduces the search space exponentially by halving it at each step, leading to a much faster time complexity of O log n for large inputs. Both algorithms share the same space complexity of O1, as neither requires additional memory beyond a few variables. The reason binary search is optimal for sorted arrays is its ability to leverage the order of elements to eliminate large portions of the search space in a single step. This makes it significantly more efficient than linear search as the input size grows. To mathematically prove the time complexity of O log n, consider the size of the search space at each iteration. Initially, the search space contains n elements. After the first iteration, the search space is halved to n/2. After the second iteration, it is halved again to n/4, and this process continues. After k iterations, the size of the search space is n divided by 2 to the power of k, or n/2 to the power of k. The loop terminates when the search space size becomes less than 1, which can be expressed as n/2 to the power of k, 1. Rearranging this inequality gives 2 to the power of k greater than n, which implies k log_2, n. Therefore, the number of iterations is proportional to the base 2 logarithm of n, confirming that the total time complexity of the algorithm is O log n. When working with binary search, there are several common mistakes to be mindful of. One frequent issue is not accounting for edge cases. For example, scenarios like an empty array, a single element array, or when the target is not present at all can lead to runtime errors. If the array is empty and your code tries to access an index like error0, you'll encounter an index out of bounds error. Another mistake is opting for inefficient solutions when dealing with large inputs. If the constraints indicate that the input size could exceed 10^5, a brute force approach will likely result in time limit exceeded errors. It's essential to choose algorithms that align with the constraints, such as binary search for its logarithmic time complexity. Additionally, off-by-one errors are very common, particularly when calculating the middle index. For instance, in languages where integer division must be explicitly handled, using low plus high /2 instead of low plus high /2 could lead to unexpected results. Lastly, if the problem includes duplicate values, failing to handle them properly can cause incorrect outputs. For example, when the middle value equals the target, deciding whether to move the low pointer with a high pointer requires careful consideration to ensure no valid results are skipped. Another common challenge is understanding problem variations. Binary search problems often come with additional requirements, such as finding all occurrences of a target, identifying only the first or last occurrence, or even working with unsorted arrays where some pre-processing might be needed. Neglecting these nuances can lead to incomplete or incorrect solutions. From an interview perspective, it's crucial to recognize patterns in the problem. If the input is sorted or partially sorted, that's often a strong hint to consider binary search as it provides efficient O log n time complexity. Communicating your thought process is equally important. Explain why binary search is appropriate, how you plan to handle edge cases, and what makes your approach robust. Interviewers are also keen on hearing your analysis of trade-offs. For instance, while brute force is straightforward and works universally, it may not be efficient for large inputs. Binary search, on the other hand, is optimal but requires the array to be sorted. Lastly, always ask clarifying questions to avoid assumptions. Verify details like whether duplicates exist, whether the input is guaranteed to be sorted, and what the expected output should be when the target isn't found. To master binary search, it helps to explore related problems that build on its concepts. A foundational example is LeetCode number 704, the basic binary search problem on sorted arrays. Once you're comfortable with that, you can tackle more advanced variations, such as search and rotated sorted array from LeetCode number 33, where the array is sorted but rotated at some pivot. Another useful variation is find first and last position of element in sorted array from LeetCode number 34, which requires careful handling of duplicates. Problems like twosum from LeetCode number 1 also introduce alternative search strategies, such as hash maps, that complement binary search techniques. When considering alternative approaches, brute force is the simplest and works in O, n, time, but it's inefficient for large inputs. Binary search, with its O log n efficiency, is ideal for sorted arrays but demands precision in implementation. Hash maps offer O, n, time complexity for lookups and are particularly effective for unsorted data, though they require extra space. Finally, two-pointer techniques are another versatile strategy, especially for problems involving sorted arrays where specific conditions like finding pairs or ranges are needed. Each method has its strengths and trade-offs, so understanding when to use each one is key to solving problems efficiently. Great job! Today, we learned about the binary search algorithm, its efficiency, and when to use it. Remember, mastering this algorithm is a must for coding interviews and real-world applications. Keep practicing, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!